Good evening. I'm Jake, and today we're here to talk about fitting vapor pressure data to the Antoine's equation. So we are looking at the Dortmund database for the vapor pressure of water. This is a subscription service for chemical compound thermophysical properties. Water is one of the free samples that they provide to give you a taste of what they have to offer. And as you can see here, they have temperature and pressure data listed through a series of temperatures, the associated pressures. But to pull data out of here manually would be a very tedious task and opens room for a lot of error. So what we're going to do instead is scrape the data from this Dortmund database using Python. To get started, we bring in all of our imports, and starting with LXML, HTML, which is the file type of this website. So we need to be able to read that file type. We're importing request, JAX, JAX NumPy, and NumPy and SciPy optimize as our coding languages to give us functions to manipulate this data with. We'll be plotting this data using Plotly. And when we are scraping the data from this website, we're going to be storing it into a dekey, which is a different form of list allowing you to append both sides. Whereas appending a normal list uses much more computing power. So this is a great way to reduce the amount of computing power you need to operate a code. We're also changing the configuration of JAX from its default 32-bit to 64-bit. This allows for double precision, and it will help us for what we're trying to do at the end. We're going to plot this data and then try and fit it to Antoine's equation by minimizing the error of our guesses. So to start off, all right, so then as you can see here, again, we're taking the URL straight from this Dortmund database website and saving it into our original URL. And then we're converting this URL into a flash-free version of it. This is what it looks like, where when we try to come and we tell our Google Collaboratory code to open this website and go through to a certain point to pull any piece of information, it runs the Flash player, fires up the website, and since we're continually doing this for a number of different values, and this is a small table, it can get much, much larger than this. We're setting up this, it's like a shadow browser to avoid overworking the site. And then that's this Git boozer content. GitHub user content, sorry. And then we're converting that file into a file that can be read by our regular expression. They're compatible. To do that, we want to have HTML.formString of this site. So then now we're setting up our regular expressions. Regular expressions are used as a type of key where each of these characters refers to the code in which this website is built on. And we're giving the XPath function specific locations to start pulling data. We're coming to this online DDB form and div2 table 3. So on here in the third table, we're looking at columns 1 and 2. It's the third figure, second table. But columns 1 and 2, and we want to pull all of the information from column 1 and save it as temperature, all of the information from column 2 and save it as our pressure data. And you can see that difference right here between the, in table 3, we're looking at the table body and the TD1 and TD2, which denotes the columns of the table here. So we have our T strings and P strings set, and we can run that. And now is where we're pulling this data from the T and P strings and saving it into a key, where we're adding in both the T strings and the P strings as integer values with the doubled precision from Jack's Float 64. So now all of our data is saved into this data variable with the first column, the first entry of this list of this key is all of our temperature values, and the second entry being all of our pressure values. So in here, we're saving a new variable as the temperature and pulling all values from the first entry into this data variable. 0 denotes the first entry, so 0 will be all of the T strings pulled into T. And we're saving another variable as the log of the vapor pressure. So on this site, we have all of our temperature is in Kelvin, which is what we would want it to be in. And then our pressure is in kilopascals. To convert kilopascals to bar, which is how the Antoine's equation is calculated, you would be finding your pressure in bar, temperature in Kelvin. We need to multiply by 1,000 before taking the log base 10. NP log 10 is a function to run the log base 10 of this value, which represents our pressure in bar. From data, 1 denotes the second entry, which is all of our P strings. So converting all of our P strings to bar, taking the log base 10 of them, and those will be our log base 10 vapor pressure values. So with both of these variables set, we can go to establishing our plot. So on here, we're plotting all of the data points from Dortmund database. This is making our subplot. We have one subplot, so 1 row, 1 column. We're adding a scatter plot to this because of the data points we've collected are just that points, so we want a scatter plot of those points with the temperature being along the x-axis and the log base 10 of vapor pressure being along the y-axis. So when this is run, you can see, oh man, that color is rough. Does that change anything? All right. Well, we have it here, and I changed these to purple. It's a bit prettier. But we have a clear relationship between the log base 10 of the vapor pressure and the temperature in Kelvin, pressure in bars. And you can see this clear decaying relationship as temperature and pressure increase. So now we're going back to this Antoine's equation. From the Antoine's equation, it's derived from the Clausius-Clapeyron relationship to create a model of the vapor pressure temperature relationship, where A, B, and C are constant values specific to the chemical species. So we're defining our model using variables A, B, C, and T, and we're returning A minus B divided by T plus C, which would be equal to the log base 10 of the vapor pressure. For our A, B, and C values, we're just using arbitrary guesses. They don't mean anything. This is because of the minimization function we're going to use. And then we save these 3 guesses into X to allow for all of our variables to be saved under one variable. When these values are saved into X, it changes their designation. So from our variable name, they are now changed to x0 is the first term we entered, x1 is the second term we entered, and x2 is the third term we entered. So 0 being A, 1 being B, 2 being C. And now we can define our square root error function where x, t, and log of the vapor pressure are our 3 variables, x containing our 3 constants, and our model vapor pressure is equal to our model up here of A, or well, using the properties or variables A, B, C, and T. And then our error is the Jack's numpy sum, which just adds up all the values we're getting for our model P minus log PV. And then we're squaring it. It's returning that error. And then our results, we minimize the square root error, save a new guess back into x0 to run through this model calculation again and calculate a new square root sum squared error. Our arguments are temperature and log of vapor pressure because we're changing our guesses. And we're allowing for tolerance of 1 times 10 to the negative 6. This is how accurate the amount of difference that we can observe of the sum squared error for this minimization to be true, for these values to match. And when we're running this at a tolerance of e times 10 to the 1 times 10 to the negative 6, it is true that these match. Our sum squared error value, the function is equal to this up here, the 0.005, and some change. So I just want to demonstrate that if we were to increase our precision limit very much, even going an order of magnitude different, we will see that our relationship is no longer true. The variance is just off enough to push us outside of our precision limits. So we're going to have that set to 6 so that we can run this nice and easily. And again, we're at true, and then it gives us our values for x, with this being our A parameter, B parameter, and C parameter. And as you can see, they're very different from what we were displaying up there. I guess 10 and 10.2 aren't that different, but the other ones changed pretty drastically. And even if we were to change these guesses, it wouldn't alter our precision that greatly. So down here, now we have our model of our vapor pressure relationship to temperature, and we're adding it to the plot of our Dortmund data bank data. And as you can see, the relationship between these two are so close to being perfect that with a simple minimization function like this, we were able to model these directly through the center of almost every data point taken. So this shows the power of this minimization technique as well as the power of the Antoine's equation. With poor guesses and a basic minimization technique, it is still able to fit the vapor pressure data nearly perfectly. Yeah, so thanks for watching, and like and subscribe.